Hello dear friends. Today in this session we will see and learn what is magnetic flux. Now actually, as we have already studied the electric flux phi E. So as we have already studied the term phi E in chapter number 1, and it is given as that E dot area or ds, and it is given as Ea cos theta, where theta is angle between electric field and cross sectional area. In exactly manner, the magnetic flux through a plane of area A, which is placed in a uniform magnetic field B as shown in figure, is given by or can be written by, here for magnetic field the symbol is used as a phi B, and it is given by exactly in a term as it was given in a electric field. Here it is written as a B dot A, or it can be extended as B A cos theta. Here also the theta is angle between magnetic field B and cross sectional area A. Here the notion of the area as a vector is already discussed, and we have also given that area vector is always coming out and perpendicular to the given plane. So the phenomena of the magnetic flux is exactly as it was given for the electric flux. So in short, we can say that magnetic field lines passing through the given cross section area is called magnetic flux. Now this was the case for the uniform magnetic field, as all the field lines B are parallel to each other. But suppose sometimes the case is like that all the magnetic field lines are not uniform, or even the surface area is also non-uniform. So for that, what we can consider over here, we can say that if the magnetic field has different magnitudes and directions at a given various part of a surface as given in this figure that is right now on the screen, then the magnetic flux through the surfaces or different surfaces, if we give them number as a 1, 2, 3, etc., then in that case flux can be given as phi B is equals to, suppose B1 is vector at some point and a small cross section area dA1 is represented for that point. Then in the same manner we take some another small segment, say B2, and related to that the cross section area will be dA2, and so on. So if we keep it continue for a longer term, we say that if there are many such points as I can show here, suppose at this point, suppose in this region also we represent some area vector, say dA1, or we can say that this is dB1 for the given portion. Then if all these type of segments are added, suppose some one is here, some component may be here, we can take as it is here. Let us consider some component at this point, so on. So suppose there are many components as given and their area vectors are there, then what we can do ultimately, so we can sum up all the terms and we can represent it in a term that is represented by the symbol sigma for all such terms which are non-uniform, and if we add them, that means it is represented by Bi I belongs to any number from 1 to n dot dai, so that I belongs to again any number from 1 to n, and that is the representation of a magnetic field for non-uniform condition. So here again I would repeat that all stands for the summation over all the area elements dai comprising the surface, and bi, vector bi, is the magnetic field at the area element dai. Now we also state something about the unit of that magnetic flux. So magnetic flux unit is Weber. It is measured in a Weber, so it is represented as WB, or if we want to write it in a spelling, we can write it WEBER. So it is WEBER. Weber is the unit for that magnetic flux. It is also has another unit, that is Tesla into meter square, because magnetic field has a unit Tesla and area has a unit meter square, so it is also represented in that way. And obviously here the term that is represented for the given magnetic flux, the dimensional formula is given. It is the same as it was given in the electric flux. So the dimensional formula is MLTA. Now we will like to repeat it. So for electric flux we write it M1 L2 T minus 2 and A minus 1. So this is the dimensional formula of magnetic flux. So this is the case of magnetic flux and how it can be defined. We would like to repeat that the Faraday had performed, and it was called as an historical experiment. So in the experiment number 1, when he pushes the magnet towards the coil, it changes the magnetic field inside the coil, and this change in the magnetic field induces EMF, and due to that EMF the current will flow through the circuit as well as from the galvanometer. In the same manner, when in experiment number 2, when he passed the current through coil number 2 and bring it towards the coil 1, then also the magnetic flux link with the 1 will change with respect to time, and due to that change in the magnetic flux, it will induce EMF in coil number 1, and again due to this EMF the current will pass through it and galvanometer show the deflection. The third experiment, if we go through that, we find that when suppose we put a coil in any of one coil, we put one rod in any of the coil, and then as shown in the figure, if coil 2 with K key pressed and we move it towards the coil 1, then the magnetic flux link with it will change and it will convert it into the rate of change of flux, and that magnetic flux will change and induced EMF will produce. In the same experiment we had also seen that if we do not change the electric current, that means key K is pressed continuously, and then if coil 2 is made stationary, then no any change in magnetic field will take place in coil 1, and due to that no any induced EMF is produced, and due to that no current will flow through that, and galvanometer shows zero deflection. See, listen properly. If key K is pressed continuously and coil 2 is kept stationary, then the current in coil 2 will not change, so it will remain constant. Due to that, the magnetic field lines coming out from it and passing through it will remain constant. That means there will be no change in magnetic flux with respect to time, and therefore for coil 1 we found no change in magnetic flux. If there is no change in magnetic field, no induced EMF is produced, and if no induced EMF is produced, no current will flow through the coil 1, and galvanometer shows no deflection. So ultimately we can finally say that Faraday's result leads us to the following statement, that is called Faraday's law of induction, and it is given as the magnitude of the induced EMF in a circuit is equal to the time rate of change of magnetic flux through the circuit. So if we go to the mathematical formula of the same, we can say that mathematically it is represented by, that is E is equals to, as per as the statement, it is d phi b upon dt, but here one additional part, that is minus sign, is introduced. Here minus sign indicates, here we will give it as equation number 1. This is our first equation of this chapter, that is also very important equation, and the negative sign indicates that the direction of EMF and hence the direction of current in a closed loop, that will be opposite to the cos, and that this will be discussed in the next topic, that is Lenz's law. So here this shows that due to the change in magnetic flux with respect to time, we get the EMF, and this EMF, if the given coil has suppose n turns, so we can say that for suppose n turns in loop, what we can say, we can simply say that EMF is equals to, minus sign remain as it is, and d phi b over dt, and this would be your next equation, that can be written as equation number 2. So both of these equations are important. Here the induced EMF can be increased by increasing the number of turns of a closed coil. Now in equation 1 and 2, we can see that the flux can be varied by changing any one or more of the terms B, A and theta. See, here it is very interesting. We have to change flux, and by the change of flux we get EMF. So how can we change the flux? So how flux may vary. This is suppose our question. So how can we change the flux? So we can say that we have equation of flux as B A cos theta. So here we have different parameters, different quantities through which we can change the flux. Here this is phi b, that is magnetic flux, and how to change it. So to change it we have three quantities are there. So suppose if we change b, so if we change b, that means if we change the direction of b or magnitude of b, we can change the magnetic flux. If we change cross sectional area, that means if one loop is given, suppose this one, now suppose loop is made smaller or the same loop is made longer, then in each case as given in the figure, you can see in this case, in this case, or in this case, in all these cases area is totally changed. So if we change the area, we can get the change in magnetic flux. And obviously third one, that is the orientation between B and A. Suppose this is your area vector and now here the B is lying somewhere here, so the angle is theta. Suppose in this case if area vector is here, here it is area vector, and suppose the magnetic field is somewhere here, then also the flux will change. And suppose in this another case, suppose B is over here and A is given here, then also the orientation between A and B changes and therefore the flux will change. So here in these three ways we can change the flux, and on the basis of that we can get the changes in EMF also. So we can change the EMF by changing the flux. So this is the EMF and the magnitude of the EMF due to magnetic induction or electromagnetic induction. Hello friends, now we will see the illustration number 1, that is 6.1, in which we are asked that consider experiment 6.2, that is given in the figure, in which one coil is given which is connected with galvanometer, and second coil is given which is connected to a power supply or a battery. Now it is given that what would you do to obtain a large deflection of the galvanometer. So suppose we are given a galvanometer and we are asked to find that what we can do to obtain a large deflection of a galvanometer. That means large deflection of galvanometer means what? It is very clear that large deflection of galvanometer means more current that will pass through the given coil. So how can we increase the current in coil 1? By changing something in coil 2. So here we are going to take induction phenomena. So in induction phenomena we know that we are not going to connect any power supply with coil 1, but we can have to change something in coil 2. So here first what we will do, we will take a small rod, suppose a small rod of say some length regarding coil, and we put it inside the coil. So if we take a soft iron rod and put inside coil 2, then whenever current will pass through it, due to that soft iron core, it will increase the magnetic field. We have discussed this case in the topic of galvanometer in the previous chapter number 4. Then what we can do, then second thing that we can do, that we can connect a powerful battery or a powerful supply with the coil 2. So coil 2 has a great power supply, a bigger power supply, can produce more current in coil 2. Due to that, the flux link with coil 1 will increase, and if it increases, we can produce more and more current in coil 1, and due to that the galvanometer will deflect more. Now third thing that we can do, that we can arrange these all things. That means we put the rod, we apply a larger amount of power supply, and third that we can do is that we can move this total arrangement towards coil 1, and therefore if we move it towards the coil 1 rapidly, it will increase the rate of change of magnetic flux, and due to that the EMF if induced will also increase, and it will increase the current inside it. So these are three possibilities that we can do. You can do another thing also, but these are the basic three things that we can do to increase the deflection of galvanometer in coil 1. Now they have also asked us the second question, that how would you demonstrate the presence of an induced current in the absence of the galvanometer. That means, suppose now we are asked that we do not use the galvanometer. So in this case, suppose in place of galvanometer we are asked to remove the galvanometer portion. So here we are given that we have to remove that galvanometer portion, and then what we can do, we remove this galvanometer and still we want to detect the current. That means, how would you demonstrate the presence of an induced current in the absence of galvanometer? Now what we can do, so it is very clear that one term that we can do and one thing we can do, that is we can connect anything like that will give us the presence of the current. Now what is the mechanism that is giving us the presence of the current? So for that we can do one simple thing, that we can connect a bulb or LED with it. So if we connect bulb or LED with it, when current will pass through it, it will glow light, and if it will glow light, we can understand that current will flow through it. So by connecting this type of arrangement, we can detect the current that passes through coil 1 without using the galvanometer. So this is your example number 1. Hello dear friends, now we will see illustration number 6.2. Now in this illustration number 6.2, what we are provided, first of all we will see that, and according to that we will find what is being asked. We are given that a square loop of side 10 centimeter and a resistance 0.5 ohm. So here the length of the loop is 10 centimeter, that can be written as 0.1 meter, and it is having resistance R, that is equals to 0.5 ohm. So here in this figure above, a red color square loop is given, which is of length 0.1 meter and a resistance of 0.5 ohm. Now it is placed vertically in the east-west plane. So here we are given east-west plane with the black color. So that black color portion belongs to east west plane and it is stand vertically in it, so it is in N to S direction as shown in the figure above. Now the given term is a uniform magnetic field of 0.10 Tesla. So here the magnetic field is also given, that is 0.10 Tesla. So this is also given information. We are provided magnetic field and the direction is also given, that it is set up across the plane in the northeast direction. So now this is interesting, they have indirectly given that the coils or the square loops vector area will be in west to east direction, it is obvious, and the magnetic field is set up in a northeast direction. So northeast direction, that means it is in between north and east. Now north and east has total 90 degree in between them, but it is in between them, that means it will form 45 degree angle with area vector A. Now it is given again, the magnetic field is decreased to 0 in 0.70 second. So we are also given a time period. We are provided a time period through which we are given that the magnetic field, initially suppose it is I, now be final, that is given 0 Tesla, so it decreases, and for that it will take about 70 seconds, 0.70 seconds. So it is given that in 0.70 second it decreases and becomes 0 at a steady rate, so that we are provided delta t also. Now from the given information they have asked us that determine the magnitude of the induced EMF. So we have to find out the magnitude of induced EMF and current during this time interval, and we are also find out to the current value of the given arrangement. So now first of all, to find out EMF we have to take Faraday's law, that is d phi by dt. Here d phi or delta phi can be given by the changes in magnetic flux. So here first of all we will take the term, that is phi 1. Now what will be the phi 1? That can be actually the phi b is represented as b a cos theta. Now this is our prime equation. Using this equation we will try to solve the example. So first we say that phi I, that will be for the initial value, so phi I, that will be bi a cos theta 1 or theta I. So bi is given, that is 0.1, or we will put these values later on. So suppose this is our phi I, in which angle is given as a 45 degree. So let's put it, we can get the value beta, that is beta I, that is 0.1. it is given. Area is given as L square, that is square loop, so it will be 0.1 square, and cos theta I is cos 45, so that will be cos 45. So now what we will get, by using this we can say this will be about 0.1 into 10 raised to minus 2. Here this 0.1 square becomes 10 raised to minus 2, and cos 45 is 1 by root 2, that means root 2 will be in the denominator. Now phi f, now they have given it that bf is actually 0, so it will be like bf cos theta f, but obviously we are given that bf becomes 0 gradually, it will be 0. So delta phi upon delta t can be written as phi f minus phi I upon delta t. So if we put this all terms with magnitude, that means if we all get the values, phi f, that is already actually 0, so 0 minus phi initial, that will be 10 raised to minus 3. Here we can put it like this, this is 10 raised to minus 3 upon root 2. So root 2 is something about value as given, and time period is given, that is 0.7 second or 0.70 second. So this term is about, this equation will be of the equation of EMF actually. So here we can say that the EMF is, that is about 1 into 10 raised to minus 3 volt. So it can be written as 1 millivolt. So the induced EMF produced over here will be 1 millivolt. Now this is the magnitude of the induced EMF. Now as per as current, we know that this is also very well known equation as Ohm's law. I is equals to E by R. We have E, that is 1 into 10 raised to minus 3, and resistance is also given, that is 0.5. So 1 upon 0.5, that will be 2 into 10 raised to minus 3 ampere, or we can say that I is equals to 2 milliampere. So for the given case, the EMF and current can be find out using this formula. Here we have to note that the Earth's magnetic field also produces a flux through the loop, but it is a steady field which does not change with the time of that experiment, and hence we does not include in the EMF term. So this is your example number 2. Hello dear friends, now in this example we are given that a circular coil of radius 10 centimeter, that is R given as a 10 centimeter, and it has 500 turns and resistance is of 2 ohm, is placed with its plane perpendicular to the horizontal component of Earth's magnetic field, that is BH. Now it is rotated about its vertical diameter through 180 degree in say 0.25 second. So we are asked to estimate the magnitude of the EMF and current induced in the coil. Horizontal component of Earth's magnetic field at a place is given by 3 into 10 raised to minus 5 Tesla. So now in this example what we will do, that first of all we will find flux 1 for the condition 1, then we rotate it up to 180 degree, then we will find flux 2, and for that we are given a time period, that is 0.25 second. So we can find out delta flux, that is delta phi. We are provided delta t, so we can find delta phi by delta t. We are given n, that is equals to 500 turns, so we can also get the value and we can put the terms and find the voltage. So first of all we will find the value for phi 1. So phi 1 is equals to, that is B into A cos theta I. Now B is given, that is 3 into 10 raised to minus 5. Area is given, that is on the basis of radius we can get area is equals to pi r square, so we can get it also. And angle is given, that is cos theta I, but initially we consider angle as a 0 degree. We can say that B into A cos 0, and therefore we can put phi 1 as B into A. So that will be your phi 1 with B atom. In the same manner, if I want to find phi 2, that is BA cos theta F, but here the final angle is 180 degree rotation, so we will have this is minus B into A. So phi 2 will be minus B into A. Now we have to find out delta phi, that is phi 2 minus phi 1. We can say that this will be minus 2B into A, and we are also given that EMF equation, that is equals to minus N delta phi upon delta T. So we can use this equation, this formula, to get the answer. Here we will say minus, we are given total number of turns as a 500, then delta phi, that is phi 2 minus phi 1, that is minus 2 BA, and upon delta T, that is 0.25. Now we will replace all the terms. We can get plus 1000 upon 0.25. Then magnetic field is given as 3 into 10 raised to minus 5. Then area is given as a pi, and r, that is 10 raised to minus 2. So here we can replace these all terms, and we can get the term as about, when we simplify these whole terms, we can say we get about 3.8 into 10 raised to minus 3 volt. So as a whole, when we simplify it, we get it as the answer, and therefore this is about 3.8 millivolt, and this will be the answer of EMF E. So here EMF will be about 3.8 millivolt. Now using this, what we can get now as a current. So we are also find out, that is current, that we have to find out by the term E by R. Here we are given resistance of the circuit also, of the coil, that is 3.8 into 10 raised to minus 3 divided by current, that is given as a 2 ohm, so it will be 2 ohm, and that is answer as 1.9 into 10 raised to minus 3 ampere. So here in this case we will given an answer that I is equals to 1.9 milliampere. So this will be our answer. So this will be upper part, that is EMF is answer 1 and current is answer 2. So we are asked to find out these two values that we have found.